Let's go through this exercise then using the 11-step guide. Step 1 was your design objectives. Well, this was specified as life safety, and it's specifically to maintain a clear lay height above the height of the people who have to pass under it. Now, as this is a public building, the clear lay height should be at least 3 metres. However, in this case, it's also desirable that smoke should not be allowed to enter any shop unit. Now, the highest shop unit is 3.4 metres. So with a clearance of 0.5 metres, we need to increase this clear lay height to 3.9 metres. So that's what we've got to maintain, 3.9 metres. Remember for later as well that the height to the ventilators is 9 metres, so your depth of your smoke layer is 5.1 metres. You will need that for later on, so remember that. So that's the clear lay height, and that's step 1, the design objectives, what we know we need to achieve. Let's move on to step 2 then. Step 2, your design fire size. Now, we're told that these are fast response sprinkler heads that are going to be put in the building. So it's the convention, if it's fast response, to assume that the largest fire size is going to be 2,500 kilowatts. Now, don't forget, if there'd been normal response sprinklers, then the design fire size would have been 5,000 kilowatts, but these are fast, so it's 2,500 kilowatts. And with fast response sprinklers, you'd assume a physical size of the fire is going to be 5 square metres, and it'll have a perimeter of 9 metres. Again, if it had been conventional normal response sprinklers, it would have been 3 by 3 metres with a perimeter of 12. These are fast response, 5 square metres and a perimeter of 9 metres. That's your design fire size. So we've moved that step, we know the design fire size. Now we need to determine the mass flow rate of smoke. Now, this is a single-storey mall, and the smoke leaving a shop will flow directly under the spillage into the reservoir. Therefore, we have to use a spill plume model. Now, the obvious model to use in this case is the single-storey mall model. However, you've got to ensure that the model's valid. To be valid, the smoke cannot rise more than 3 metres before reaching the base of the smoke layer. Now, in this case, we've already established that the clear layer height is going to be 0.5 metres from the spillage at the highest point. So, in other words, this formula is valid. You can use it. And this is a formula you should have used. M smoke equals CE times P times Z to the 1.5, where CE is your coefficient of entrainment, your P was your perimeter of your fire, and Z is the clear layer height. So let's put in our variables now. The coefficient for a single-storey mall with a height of rise of less than 3 metres is 0.38. Now, the perimeter is 9 metres and the clear layer height is 3.9 metres. If you put them in, you should have got a mass flow rate of smoke of 26.34 kilograms a second. So that's worst case out of the highest point, out of the shop, 26.34 kilograms per second. So, we know how much smoke's been produced, but now we need to work out how hot it is. Let's move on to step 4. Step 4, determining the temperature of the smoke. This is the formula you'd apply. Theta equals QP divided by MC, where theta is your temperature rise, QP was your convective heat output, M was your mass flow rate of smoke, and your C was your specific heat capacity of air. If you'd have put in those in the formula, you'd have got a theta of 94 degrees Kelvin. So that's the increase in the temperature of the smoke. Now we need to work out the absolute temperature of the smoke layer using this formula, where TL equals T0 plus theta. And if you'd put them in, you'd have got a TL, a temperature of the smoke layer, of 382 degrees Kelvin. Now, don't forget, it's important to remember at this time that there's a life safety system, and the temperature of the smoke cannot exceed 200 degrees C. So if we convert the temperature to degrees C, we get 382 minus 273, so it would have been 109 degrees Celsius, which is well below what we classify as tenable. So that concludes this step. Let's move on to step 5. Step 5 is the stratification check. Now, in this case, because the clear layer height is so low, in other words, only 3.9 metres, then stratification can be ignored as it's not a problem. It's not a problem with such low heights. You don't have to carry it out at those heights, 3.9 metres. We can move straight on to step 6, which is determining the ventilation requirements. Now, it's been decided to use mechanical ventilation in this stage, and therefore we're going to proceed with that in mind. They want to use mechanical ventilation. Now, we need to determine, first of all, how many reservoirs we need. Now, the largest size of a reservoir in a mechanical system is 2,600 square metres. Now, in this case, it tells us that there's 2 reservoirs, 6 metres by 50 metres, which is well below the maximum. Well below the maximum. And next, because we're looking at mechanical ventilation, we don't need to work out the aerodynamic free area, we've got to work out the volumetric flow rate of smoke, and this is based on our design fire size. So we've got to work out the actual volumetric flow rate. To determine the volumetric flow rate, you use this formula here. V equals M divided by rho times TL divided by TO, where your V is your volumetric flow rate in cubic metres a second, M is your mass flow rate in kilograms a second, your densities in kilograms per metre cubed, TL is the absolute temperature of the smoke, and TO is your ambient air temperature. If you'd have put in your known variables, you'd have got a volumetric flow rate of 29.03 metres cubed per second. So that covers step 6. We've worked out the volumetric flow rate. Now we're going to look at step 7, determining the number of ventilators. Now it's proposed, as we said in the question, they're going to have fans of a capacity of 10 metres cubed per second are going to be used. Now in this situation, because the automatic fans will be located in an atrium which will have no fire loading, it can be assumed that no fans will be lost in a fire. And we also know the volumetric flow rate is 29.03 metres cubed a second. With fans having an output of 10 metres cubed a second, we need 3 fans. So that's all we need. We don't have to take one out in a fire. We need 3 fans located symmetrically down the reservoir. So that's how many actual ventilators we need. That covers step 7. Now we can move on to step 8, which is the stagnation check. Now, because this is a mechanical system, then the stagnation check does not apply. It only applies to natural systems. So again, we can kick this step out. We can move straight on to step 9, which is the plug hole-in check. Now, this does apply to both natural and mechanical ventilation, so we do need to work out the plug hole-in check. Now don't forget there's 2 models to determine if plug holing will occur, and this depends on where the ventilator is located. There's 2 models, one when it's nearer than 2 metres from the edge and one when it's more. In this case, clearly, based on the fact you only need 3, they're going to be more than 2 metres from the edge of the reservoir, and this is the formula you are going to apply to work out the plug holing requirements. MCrit equals 2.05 times rho 0 times G TO theta to the power of half, or the square root, D squared WV to the half, all the whole lot divided by TL. If you'd have put them in, your known variables, you'd have got an MCrit of 81.89 kilograms a second. So if more than 81.89 kilograms a second is going out of any ventilator, this is just one, been extracted out of one, it will plug hole. Now we know the MCrit, which is in kilograms a second. Now we need to work out, because the fans are rated in cubic metres a second, we've got to convert that into kilograms a second. And this is the formula you'll apply. M fan equals V fan times T naught rho 0 to the TL. Put them in, you'd have got this. M fan equals 10 times 288 times 1.2 divided by 382, which means the fans are rated at, for this particular temperature of smoke, at 9.04 kilograms a second. That's how much smoke each fan will be extracting, which is much lower than the critical exhaust rate, and therefore plug holing is very unlikely to occur. So you've passed the plug holing check. That covers step 9. Let's look at step 10 now. This is to check the air inlet velocity if required. So this final check which has got to be done is to ensure that the replacement air coming in through the exit doors is not so high as to impede escape from the building. Now this is a shopping centre, so on the assumption that the public will resort to the building, the maximum velocity that is allowable for the incoming replacement air is 5 metres per second. We don't have a figure for the area of the inlet vents that will provide replacement air, so what you should have done is determined the minimum required area. So you're going to say what the minimum required area is, and they've got to provide this. Now if all the fans are working, in other words, none of them are broken down, which in this case is natural to assume, there's no fire loading right next to them, 3 fans are going to run at their rated output. So you've got 3 fans at 10 cubic metres a second, which gives you a Vmax, a total extraction rate, if they're all running, at 30 metres cubed a second. This is the formula you should have applied. AI must be greater than or equal to Vmax divided by U divided by CI, where AI is your aerodynamic free area, your Vmax is the fact for all the fans running, the maximum capacity of all the fans running, U is your maximum velocity allowed, and CI is the coefficient of the inlets. If you'd have put them in this formula, you should have got an AI of greater than or equal to 10 square metres. So in this exercise, you need at least 10 square metres of doors that must be automatically opening or automatic opening vents to replace the air that's been sucked out. That's a minimum 10 square metres. That's the minimum. If you'd have had more than that, it'd have been less, but if you'd have had less air than that, less inlets than that, then the velocity would exceed it and it does have an impact on the means of escape. That completes this step. The final step is step 11, post-design considerations, and in this case you've still got to consider the impact of wind, because if wind is a significant factor you might want to increase the extraction rate to overcome this, and you look at things like curtains and your testing and your maintenance. That's your post-design consideration. That completes this exercise.